Alright gang, here we go. So this is Chem 2, Unit 4. We're going to be talking about acids and bases in this video. Later on in the year, we're going to have a whole unit about acids and bases, and we're going to learn a lot more about them. So right now, this is just kind of like the briefest of tastes about what acids and bases chemistry looks like. Alright, acids are defined for now as any substance that when they ionize in aqueous solution, remember this means they form ions, okay? In aqueous solutions they form H+. All right, H+. Now this is equivalent to saying they form H3O+. This is our hydronium ion, because that H+, when it's in solution, it's not just a little proton that's floating around, it actually gets attached to the water molecules that are in there because you're in an aqueous solution, right? Okay. And so essentially, because this is only an extra proton that's in solution, a lot of times we'll refer to acids as proton donors because they started with a proton and then they're giving it up. They're donating that proton away. All right, so here's a whole bunch of different acids: hydrochloric acid, nitric acid, sulfuric acid. Notice that all of these acids start with this H value over here. All right, and notice that these H's are kind of sticking off the end of our molecules, right? They're just kind of chilling there, and they'd be easy to pull off. They're easily accessible, easily gotten rid of. Okay, this guy's acetic acid. Okay, now notice that it doesn't start with the H, right? The H is missing from the front of this guy, but because it's got this little thing right here, this is called a carboxylic acid group. Remember when we talked about organic nomenclature? So this is a different group, kind of like the alcohols, right? But it's got this guy here attached to it, and so this hydrogen right here is the acidic hydrogen. That's the proton that'll come off. So anytime you see a molecule that's labeled with an H in the front or COOH at the end, that should tell you that you're dealing with an acid. All right. Bases that react with or accept those hydrogen ions. Okay. All right. So a lot of times these are called proton acceptors. Okay. All right. So proton, I'll just say P plus acceptors. All right. So they react and they accept that hydrogen that the acid gave off. You can also define them as increasing the concentration of hydroxide, all right, when dissolved in water. So either way, okay, we'll kind of look at both of them here in a second, okay. Now notice that, so if they have the hydroxide, then they'll donate that in order to increase the concentration of hydroxide, and that's the base. Okay, but down here, notice that we have ammonia, okay, and water will give up this hydrogen attached to the ammonia, and then it increase the concentration of hydroxide, and it also accepted that proton. So that's why ammonia is a base, because it increased the concentration of hydroxide even though it didn't have that hydroxide attached to itself. So make sure you're paying attention to that, okay? All right, so now we have to be able to identify whether or not we're dealing with a strong acid or a weak acid, because they're going to act differently in water. Okay, remember a couple of videos ago we talked about strong versus weak electrolytes? So same kind of idea here. Strong acids completely dissociate, right? So that means when HCl is one of our strong acids, when that reacts in water, it's going to form H plus and Cl minus. Okay, so you get every single molecule of HCl that you started with is going to be floating around in solution as either an H plus ion or a Cl minus ion. Okay, weak acids do not do the same thing. They only partially dissociate. So like if you had your acetic acid, this is a weak acid. Okay, when this goes into water, it forms an equilibrium of acetate, CH3COO minus, as well as H plus. Okay, and we'll talk about, as I keep saying this, the next semester when we talk about acids more in depth, we'll talk a lot more about what this means for our chemistry. All right, strong bases dissociate to metal cations and hydroxide anions. All right. Weak bases will only partially react to produce the hydroxide. So it's the same kind of thing here. Strong acids completely dissociate, strong bases completely dissociate, but weak bases don't really dissociate, they more react to form hydroxide ions, kind of like the NH3 from before. All right, so here's your strong acids and strong bases. You do need to memorize these, okay, and I'm going to teach you a trick to memorize the strong acids. Strong bases is super easy. It's all the group, anytime you have a group 1A metal, okay, so that's the first column. Those are alkali metals. Anytime they're paired with a hydroxide, they're automatically strong. Okay, so lithium, sodium, potassium, rubidium, cesium, strong bases. All right. and then the column right next to it, the alkaline earth metals, the heavier ones form strong bases. So beryllium and magnesium are not defined as strong bases, but calcium, strontium, and barium are defined as strong bases. All right. So bases are easy. Essentially, it's the first two columns paired with hydroxide, except for beryllium and magnesium. All right. Strong acids can be a little bit tougher, so I'm going to teach you a method to memorize them. Okay, so there's 7 of them, right? So we could just label these 7. 1, 2, 3, 4, 5, 6, 7. Okay, so these are our strong acids. All right, so you're going to start off by saying hi, chlorine and bromine. There are 3,344 of you. Okay, high bromine, or high chlorine and bromine, or you could do bromine and chlorine. High chlorine and bromine, there are 3,344 of you. 2 of you are ClO. Are the other 2? No. There's something else. Okay, so high chlorine and bromine, there are 3,344 of you. These 3s and 4s are subscripts here. 2 of you are ClO, right? And then are the other 2? No. There's something else, okay? And then we're going to add hydrogens to all of them. Straight down the list, everyone gets 1. And then at the end, we're going to double check it by writing in a 2. Okay, so those are strong acids. So one more time, you ready? High chlorine and bromine. There are 3,344 of you. 2 of you are ClO. Okay. Are the other 2? No, you're something else. And then I'm going to add hydrogens and then double check. All right, so there's your strong acid. This is really dumb, but you won't forget it, okay? So now, based off that, we have to decide whether or not we have a strong or weak electrolyte, okay? Anytime you have an ionic compound, it's automatically a strong electrolyte. And so, yes, that even includes the ones that are insoluble. So remember last video we talked about solubility rules and all that. Even if it's insoluble, that's still defined as a strong electrolyte because every bit of it that has dissolved in water is going to be a ion. So therefore, it's a strong electrolyte, okay? So anytime you have an ionic compound, remember, so that's a metal with a nonmetal, automatically strong electrolyte, easy peasy. Now, if you have a molecular compound, you have to ask yourself if it's an acid or a base. If it's not an acid or a base, okay, you automatically know it's a non-electrolyte. Okay, so if you have a molecular compound and it's not an acid or a base, it is a non-electrolyte. Okay, so then you know it's an acid because it's either starts with an H or ends in COH. All right. And then if it's not on the list of our strong acids, you know it's a weak acid. All right, strong acids are strong electrolytes and weak acids are weak electrolytes. Okay. Strong bases, if it's a base, then you have to look at your table, the table we just looked at, okay? The strong bases, those are the first 2 columns, right? First 2 groups attached to hydroxide except for beryllium and magnesium. Those are strong electrolytes. So our strong bases are strong electrolytes. And then also know the one tricky one that you might forget is NH3, and that's a weak base, all right? So here's your little table helping you summarize, all right? So ionic compounds all of them are strong electrolytes. Strong electrolytes, molecular, strong bases, and strong acids. Weak acids, weak bases, and then all other compounds, all right? So we're going to do a little practice here. We're going to identify whether or not it's a strong electrolyte. So ammonia, well, that's NH3, okay? NH3. And so that was a weak base. That was one of the ones we had to have memorized. So this guy would be a weak electrolyte, all right? So I'll just put a line through that saying that it's not a strong electrolyte. Hydrofluoric acid, well, that's hydro means it's just the element by itself, fluorine, so HF. And so is HF in our strong acids? Well, no, it's not, right? So therefore, it is a weak acid because it starts with an H and it says acid right there. And so therefore, it's going to be a weak electrolyte. Okay, folic acid, this is B9, okay, the vitamin, B9. Anyway, folic acid is a molecular compound, but it's not one, and it's an acid, but it's not one of our 7 strong ones, so therefore it is a weak electrolyte. Sodium nitrate, well, this would be NaNO3, and we know this is an ionic compound, right, because it's going to form ions, and so therefore it's going to be a strong electrolyte because it's an ionic compound. And then sucrose, that's sugar. This is a molecular compound. It's not one of our strong bases and it's not one of our strong acids, and so therefore it can't be an electrolyte at all. So this guy's actually going to be a non-electrolyte, so I'll put 2 X's through it. All right. Neutralization reactions happen when you have an acid and a base that are reacting with one another. All right. So there's certain ones that I'm going to ask you to be able to predict the products for. All right. When the base is a metal hydroxide, okay, and it's reacting with the acid, you get water and a salt. All right. So it's a metal hydroxide. So that means you got a metal attached to a hydroxide. You're always going to form the same 2 compounds, water and a salt. Now remember, a salt is defined as any ionic compound. So this is metal with a nonmetal. All right. And so we can actually write these as molecular complete ionic or net ionic equations. So here's our molecular equation right here. So this is a classic example of hydrochloric acid reacting with sodium hydroxide, and it forms water and sodium chloride, which is just table salt. All right, so there's your water and there's your salt, your 2 products, and there's your metal hydroxide. Complete ionic, we take everything that's aqueous and split it up. So notice that we form all these ions from our acid and our bases. Our water is not ionic, so it's not going to split apart. It's just going to stay as liquid water right there. And so everything that's spectators, we'd cancel them out, so we'd be left with this guy here. All right, you could play around with this, do a couple of different examples. Anytime you're reacting a strong acid and a strong base, or you're always going to have the same net ionic equation. It's always going to be some variation of that, just forming water essentially. Okay. Now there's 2 different types of reactions that I want you to know that are neutralization reactions that form gases. The first, okay, is when you react if you have a carbonate or a bicarbonate. Okay, and when that reacts with acid, you're always going to form the salt. Okay, but then you're going to form carbon dioxide and water as your other 2 things. All right, so here's calcium carbonate, right? CO3 is our carbonate, and it's reacting with an acid here. It's going to form the salt, right? So that would be the chlorine and the chlorine and the calcium would react together, form that salt. But then instead of forming H2CO3, which would be another acid, it's going to form carbon dioxide gas and water. And if you remember, back in Chem 1, we probably did this reaction where we took a piece of chalk, right? And we added some acid to it. And so that chalk is essentially calcium carbonate. We added a little bit of acid to that, and you could see it bubble up. And the bubbling was the carbon dioxide that was being formed. All right, here's sodium bicarbonate. If we act that with an acid, we form the salt, right here, sodium bromide. But instead of forming H2CO3, again, that carbonic acid, we form carbon dioxide and water. All right, so that's the first reaction that you need to just make sure when you're doing a neutralization reaction that you check to make sure you're not reacting a carbonate and a bicarbonate, because if you are, you're going to be forming carbon dioxide gas. All right. Finally, all right, last little bit here, if you're reacting something that has sulfur attached to it, okay, so this would be sodium sulfide with sulfuric acid, you're going to form the products that you'd expect, sodium sulfate and H2S. But be warned, H2S is a gas, okay, so it's hydrogen sulfide gas. You want to do it a fume hood because it smells like rotten eggs, and it's also poisonous if you get enough in you. All right, so you got to watch out for that. So you need to make sure you understand that if you're reacting, if your base, okay, if your metal that's reacting with your acid has a sulfur in it, then you'll be forming hydrogen sulfide gas more likely, and you got to watch out. All right. Here's a bunch of just common antacids, okay? So neutralization reactions, so if you get heartburn, something like that, that's really just your body producing more than its fair share of stomach acid. And so it feels like it burns, whatever. And so then you can take any of these guys here, and these are just essentially bases. Notice that a lot of them have these magnesium hydroxide as one of the bases that are in it. If you take Tums, it's calcium carbonate. So if you notice that you're reacting that and you feel like you're burping a lot after you do it, that's the carbon dioxide gas that's being produced inside your stomach and escaping. Anyway, so it's kind of fun. We'll mess with milk and magnesia in class a little bit. All right. So here we go. Net ionic equation for the reaction of ammonia and nitric acid. All right. So let's see if we can figure this guy out. So ammonia is NH3. Okay. NH3, and we're going to react that, and it says it's aqueous, so we'll throw that AQ in there just to make him happy, and it's reacting with nitric acid. Well, this ick, remember you ate something icky, so this would be HNO3, okay, and acids are always aqueous, all right, and that's going to react to form, well, we're going to form NH4 plus ammonium, okay, and this guy's going to be aqueous, and then we're going to form NO3 minus, and this will be aqueous. All right, so and so then we could split these guys up into their ions, right? You got NH3, okay, isn't going to form an ion, but then you get H plus aqueous plus NO3 minus aqueous. All right, and that's going to form NH4 plus aqueous, and this guy's not going to split up, plus NO3 minus aqueous. Oh, I've run out of room. So this NO3 is going to cancel here, okay, and then everything else is going to be left. So we'll be left with this NH3 aqueous plus H plus aqueous. It's going to react to form NH4 plus aqueous. All right, so there's our net ionic equation. Let's see if it's one of our options here. And so, yes, it happens to be D right here. All right. So anyway, so there's a couple practice, or another practice problem that you can work through. Let me know if you have any questions. Do your homework, and I'll see you on the flip side.